summarize what we've been learning about function transformations. And I'm going to start with this very familiar function, the absolute value function. We call this the parent function of the absolute value function family because it's the simplest. Uh, it's like the simplest version of an absolute value function. And you guys probably know that or recall that we can do all sorts of things to this absolute value function, like scale it, shift it to the right, and maybe shift it down like that. So let me pick a different value here, just so we have different numbers. So what we've done is we've taken the original absolute value function and we've shifted it to the right 3 units, down 4 units. That's what this 3 and 4 do. And then we've stretched it by a factor of 2. So instead of going up 1, over 1, up 1, over 1, from the vertex we go up 1, up 2 over 1, up 2 over 1. And what I'd like to do here is kind of generalize this. Imagine instead of minus 3 right here, I just put minus h. Desmos prompts me to add this slider. And then I can slide this thing either in the positive direction, so it'd be like h minus 5, that would shift it to the right 5 units, or h minus a negative 3, which is like h plus 3 really, shifts it to the in the negative x direction. So now I got a slider, and what's happened here is my relationship has become a little more general. It just depends on this parameter h, and then I can, whatever h is, I know what that's going to do. It's going to cause a horizontal shift. I'm going to do the same thing here by adding a vertical parameter k, and if I do plus k, then this behaves just as I imagine it should. Positive k shifts vertical in the positive vertical direction, negative k shifts the graph down. And then finally, I'm going to put this last parameter. There it is, a. And of course, as a increases above 1, we start to get a vertical stretch. And then when a is like between 0 and 1, it causes a vertical compression. And then when a goes negative, it causes a reflection of my graph across the x-axis. So A handles a few things. It causes stretching, compression, or reflection. And so now I've got a very general absolute value equation here for g of x. And depending on the values of a, h, and k, my graph may be scaled and reflected. It might be shifted to the left or to the right, and it might be shifted up or down, however much I choose. And I want to go one more step here. And instead of actually evaluating the absolute value here, what I'm going to do is I'm going to just change it like this. So now instead of a times the absolute value of the quantity x minus h plus k, I'm just doing whatever this function is f, I'm transforming that using these parameters. And notice it behaves in the same way as it was before. So a vertical shift and a horizontal shift. But what's interesting about this now is that if I change my function f, then all of these parameters will still do the same transformation to the resulting function. So for example, if I, instead of absolute value, I said f of x equals x squared, well now a times f of x minus h plus k is basically taking the original parent function of the quadratic function family, and it is stretching it, or that is scaling it in the vertical direction, either stretching or compressing. And if a goes negative, it reflects. And then I can do a vertical translation and a horizontal translation. So whatever function, I could even start off with, something like some cubic. I don't know a lot about what graphs of cubics look like, but there's the red function f, and I just kind of made up this cubic. And then sure enough, if A will stretch the function in the vertical direction or compress it and eventually reflect it. K will cause a vertical translation and H will cause a horizontal translation. And I can show that this works in the same way by lining the function back up. When H is 0 and when K is 0 and when A equals 1, then G of X is just the same as F of X. This would be, if A was 1 and H and K were both 0, this would just say G of X equals F of X. And there it is, the graph is right on top of the other graph. So what's really interesting about this, I think, is that no matter what your original function is, you can translate it with an H and a K, and you can stretch it or reflect it or compress it with A. And I've summarized this relationship, and I encourage you to try this with Desmos, and it doesn't take very long, but I've summarized this basic information about function transformations here on this slide. So here, the function g of x is a transformation of the function f of x. And it describes what each of these three parameters does to the original graph of f of x to get g of x. So starting with h, it says h causes a horizontal translation, and if h is less than 0, the translation goes to the left. And notice that's because I put a minus sign in my function here. And so when h is negative, this turns into a plus. And when h is greater than 0, we get a horizontal translation to the right. K causes a vertical translation, and that behaves according to our intuition. And then the A causes a vertical dilation and reflection. So a dilation is either a stretch or compression, some kind of scaling. And when the absolute value of A is greater than 1, we get a stretch. And when the absolute value of A is between 0 and 1, we get a compression, that is ignoring the sign. And then if A is less than 0, in other words, if A is a negative number, we're going to get a reflection, a vertical reflection across the x-axis. And that's a good summary of how to transform the graph of f of x into g of x and how that transformation is represented in the equation.